So, we will be discussing more on memory management and arrays. And this will be the last topic of arrays. After that, we will be discussing multidimensional arrays in a little detail. Let me just adjust my microphone first. After that, we will be discussing multidimensional arrays in a little detail. Then we'll be moving to the next topic, right? So let's proceed. So, memory management in arrays, right? Memory management in arrays is kind of simple and kind of complex at the same time. So memory management is a crucial aspect of working with arrays in programming. Understanding how arrays interact with memory, right? So that you can know how to manage it as well. You need to know how it works for you to manage it properly. Right. So, understanding how it interacts with memory can help you write more efficient code, avoiding some common pitfalls like memory leaks, optimize performance. So a detailed look at memory management is like first we have talked a lot about contiguous memory allocation. So how is it stored? How it works, right? How arrays are stored? So arrays are stored in a contiguous block of memory. This actually means is that all elements of the array are stored one after the other in memory with no gaps in between. So for example, if you have an array of 10 integers, all 10 integers are stored in a single block of memory, right? So that's how arrays are stored. Then you have efficiency. Contiguous memory allocation is efficient because it allows for fast access to elements using their indexes. Since memory address of the first element, often the base address, is known as the address. So that is known, so the address of any other element can be calculated very quickly and efficiently and directly. For instance, the address of the fifth element in an array can be determined by adding an offset to the base address, making element access to an O1 operation. Right. Then we have static and dynamic memory management in arrays. Static arrays have a fixed size, right? They have fixed size. When you declare a static array, you must specify its size up front. So the size is it cannot be changed during runtime, and the memory for the entire array is allocated at once when the array is created. Then you have something called memory efficiency in static arrays. Well, static arrays are simple and fast. They can be inefficient in terms of memory if the exact size of the array is not known in advance. So allocating an array that is too large can waste memory Well, an array that is too small might lead to overflow issues. Um, we have also stack allocation in many languages. Stack arrays are located on the stack, which is a region of memory that has limited size but allows fast allocation and delocation. Then you have something called dynamic arrays. Right. So dynamic arrays are resizable. Dynamic arrays like those implemented in higher level languages like Python list or Java's array list can change size at runtime. So this flexibility comes with additional memory management responsibilities. Heap allocation. These dynamic arrays are typically allocated on the heap, a memory area that allows for flexible and larger allocations of memory. Memory on the heap must be managed carefully to avoid leaks, right? Then you have reallocation. When a dynamic array exceeds its initial capacity, a new larger block of memory is allocated, right? And the contents of the old array are copied to the new block. This process is called relocation or reallocation and can be expensive in terms of time and memory, right? But it's necessary to accommodate the growing array, so you have to do it. Then we have some challenges, right? So many memory management challenges, memory leaks in languages that require manual memory management like C++ or C. Dynamically allocated arrays must be explicitly declared or deallocated using functions like free in C. Right? Failure to do so can result in a lot of memory leaks and a lot of memory mismanagement. So where that memory is no longer needed, and it's not released to this back to the system, eventually exhausting the available memory. That's just something which is memory leak. You're allowing the memory to be wasted rather than being used, right? So yeah. Then we have something called fragmentation in systems, right? In systems with heavy dynamic memory allocation and deallocation, memory can become fragmented. So this happens when small non-contiguous blocks of memories are free, but no large enough block is available to satisfy a new allocation request. Basically, fragmentation can lead to inefficient memory usage and slowdowns. Right, so this can happen when heavy memory allocation and deallocation have been happening. So memory can become streamlined, fragmented, right? And we have garbage collection. In languages with automatic memory management like Java and Python, garbage collection handles the deallocation of memory, right? However, understanding how garbage collection works is important, as the inefficient use of garbage collections and arrays can still lead to performance problems like unnecessary memory retention or slowdowns during garbage collection cycles. Then you have something called RSIs, memory concentrations. Choosing the right size is important in arrays. When declaring an array, it's important to choose an appropriate size. Allocating too much memory can lead to waste, while delocating too much memory can lead to allocating too much memory can lead to waste, and allocating too little can result in overflows or the need for costly reallocations, right? So then you have capacity versus length. In dynamic arrays, capacity refers to the amount of memory currently allocated, right? While length refers to the number of elements currently in the array. When the length exceeds the capacity, the array must be resized, which involves allocating more memory and copying the existing data, right? A process that can be slow and inefficient if done frequently. Then you have some memory management alignment. Memory alignment refers to how data is arranged and accessed in memory. Proper alignment is crucial for performance, as modern CPUs are optimized to access data that is aligned in specific boundaries, like 4-byte boundaries for 32-bit data, right? Padding. You have something called padding. In some cases, compilers might add padding to arrays to ensure proper alignment, especially when arrays are part of larger data structures. This padding is usually invisible to the programmer, but is important for ensuring that array accesses are fast, efficient, and reliable. So you can also optimize your memory usage. You can minimize your memory footprint. To optimize memory usage, consider the size and type of data stored in arrays. For example, using longer data types, int versus long, can reduce the overall memory footprint of the array. You can also reuse arrays. Reusing arrays rather than creating new ones can help reduce the overhead associated with frequent memory allocation and delocation, particularly in performance critical applications. Then you have something called memory pools. For applications that require frequent creation and deletion of arrays, using a memory pool can be more efficient. A memory pool is a pre-allocated block of memory from which arrays are allocated and delocated, reducing the fragmentation and improving performance, right? So there are also some advanced techniques like array slicing. Some languages support array slicing, where a sub-array is created by referencing a portion of the original array. This is memory efficient because it does not require copying the original array, but care must be taken to manage the original array's lifetime. Then we have something called sparse arrays. In cases where most elements of an array are 0 or empty, using a sparse array which only stores non-empty elements can significantly reduce memory usage. Memory management is critical aspect of working with arrays. Understanding how it works, how arrays are stored in memory, the differences between static and dynamic arrays, the challenges of memory management can help you write more efficient and robust programs. By considering factors like memory allocation and fragmentation and alignment, you can optimize the use of arrays in your applications. ensuring they run smoothly and efficiently. There are one-dimensional arrays in programming. One-dimensional array is the single array that I told you about, right? One-dimensional array, often simply called an array, is one of the most basic and essential data structures in programming, right? So this is kind of a one-dimensional array, right? It's the basic and the most essential data structures in programming. It consists of sequences of elements stored in contiguous memory locations, all of which are accessible through using a single index. And the definition and the structure of the one-dimensional arrays are very simple. One-dimensional array is a linear structure, meaning it is a single row, right, or a single column of elements or list of elements, where each element is indexed by a single integer value. For example, an array of integers like this can be represented as 1, 2, 3, 4, where each element where each number is an element in the array. You can also use indexing in this. Elements in one-dimensional array are accessed using an index, typically starting at 0 in most programming languages. So the index represents the position of the element within the array. For example, in the array 10, 20, 30, 40, 50, the element 30 is at index 2, right? For this array 1, 2, 3, 4, the number 2 is at element 1, 1 at element 0, 3 at element 2, 4 at element 3, right? Sorry, the element 1 is at index 0, the element 2 is at index 1, the element 3 is at index 2, and the element 4 is at index 3. Right. So array declaration and initialization. To use an array, it must first be declared with a specific size, which determines how many elements the array can hold. The size of the array is usually fixed in static arrays. In dynamic arrays, the size can change as needed. When you have initialization after declaration, arrays can be initialized with values. For example, in an array of 5 must be initialized with the values 1, 2, 3, 4, 5. If the array is not specifically declared or initialized, the elements must be set to default values like 0 for numeric types, right? Then accessing the elements is also one of the major things. Index-based access. We have index-based access in a one-dimensional array. Accessing an element in a one-dimensional array is a straightforward method or approach using its index. If R is an array, then R1I refers to the element at the ith position. This access operation is very efficient with a time complexity of 0, 1, meaning it takes constant time regardless of the array's size, right? The time it's actually written as O 1, right, 1, which means it takes constant time regardless of the array size. So the time complexity is 0, 1, which will mean that it will take a constant time for every array in regardless of its size, right? So modifying elements, you can modify an element in an array by assigning a new value to it using its index. For example, arn2 equals to 10. The third element in the array at index 2 will be updated to 10, right? Then some common operations on array. Iteration. One of the most common operations on a one-dimensional array is iteration, where you loop through each element for the array, typically for using a for loop. This is useful for processing or analyzing the data stored in the array. Right? When you are searching, you can search for a specific element in the array using algorithms like linear search, where you iterate over the array until the element is found. In a sorted array, binary search can be used for faster retrieval. Sorting is used for sorting an array. It rearranges its element in a specific order, ascending or descending. Common sorting algorithms include quicksort, merge sort, published sort, bubble sort. Sorting is often required to optimize search operations or prepare data for analysis. Inserting and deleting elements in static one-dimensional arrays. Inserting or deleting elements can be costly because it may require shifting other elements to maintain order. Let's say, for example, you inserting an element in an element at the beginning of the array, and it requires shifting all existing elements to the right. So there are some advantages of these one-dimensional arrays, which is this. First is simplicity. One-dimensional arrays are simple to use and great to understand, making them a great choice for beginners and straightforward tasks, right? Efficiency. Due to their contiguous memory location, arrays allows fast access to elements using indexes, which is crucial in performance-critical applications. Then you have predictability. Arrays provides predictable behavior in terms of memory usage and performance, as the size is fixed and access times are constant. There are some limitations of arrays, one-dimensional arrays. Fixed size. In most programming languages, the size of an one-dimensional array is fixed upon creation. If you need to add more elements than the array can hold, you will need to create a new larger array and copy the old elements into it, which can be inefficient at this time, right? Then we have something called homogeneity. One-dimensional arrays typically hold elements of the same time, which means this you cannot mix different types of data, integers and strings, into the same array, right? This is an int array, right? So you cannot mix different types of data in the same array. Then you have insertion and deletion, overheads. Inserting or deleting elements except at the end of the array is inefficient because it involves shifting elements, which can be costly in terms of time, especially for large arrays. You have real world applications of these arrays. Data storage. One-dimensional arrays are often used to store lists of data such as a list of scores, names, or any other sequence of values. Then you have buffering. Arrays are used for as buffers in data streaming or networking, where they temporarily hold data before it is processed or transmitted. Then you have mathematical computations. In mathematical applications, arrays are used to store vectors and sequences of numbers for various computations. An example use case can be like you can consider a simple program that needs to store, and calculate the average of student X scores. A one-dimensional array is an ideal candidate for this. It's an ideal structure to store the process because you can easily access and each score using this index, right? This particular index, and iterate through the array to sum the scores. Then divide the number of the elements to get the average. There are some best practices that you need to take care of, right? Initialize properly. Always ensure and check if the array is being initialized properly, right? To avoid unexpected behavior. Choose the right size. If possible, estimate the size of the array based on expected usage to avoid wasting memory or running out of space. Use dynamic arrays for flexibility. If the array is not known in advance or if it will change frequently, consider using dynamic arrays or other data structures like linked list, right? So one-dimensional arrays are a fundamental structure, right, for in programming, offering a very simple and efficient way to store and manipulate linear collections of data. Understanding how it works is very crucial, right? Because if you have to understand that these are very basic forms of code, right? Understanding how to use them effectively is crucial for solving a wide range of programming problems. Create a lot of complex structures from basic data storage to complex algorithm tasks, and despite their limitations, their simplicity and efficiency makes them an indispensable tool in any programmer's belt, right? Because even though they are very simple, they are very, very important, right? So that's why one-dimensional arrays are very important. Now we'll be discussing about two-dimensional array. Two-dimensional array or a 2D array is actually an extension of the basic structure of the basic one-dimensional array, where data is organized in a grid or matrix-like structure. This data structure is incredibly useful for representing tabular data, right? Images, matrices, and more. So a detailed look at the use of one-dimensional array would be like, firstly, and how they are managed is, firstly it's managed like in a grid-like structure. It's kind of a matrix, right? So let's start like this. Then you have two variables, 3, 8. Then you have 5, 6. Then you have 4. Right. So you can visualize a two-dimensional array as like this. A two-dimensional array can be thought of as a grid with arrows and columns. Each element in a two-dimensional array is accessed by two indexes, right? One for the row, one for the column, and a 3x3 matrix can be visualized like this. If you go more, 7, 8, 9. So this is a 3x3 matrix, right? So the element 5 is located at the second row and second column, often accessed as this value R1, 1, right? Assuming zero based indexing, right? The first part is 0, right? So there are some row major versus column major order. So row major order in most programming languages, two-dimensional arrays are stored in row major order, meaning all elements of the first row are stored sequentially in memory, followed by elements of the second row, and so on. So basically that means this two-dimensional arrays are stored in row major, meaning all elements are stored in the first row and sequentially, like order by order, followed by the second row of the third, and so on, right? Then you have column major. Some languages like Fortran, actually it's a very difficult name, but we do have some languages like these which use column major order, where elements of each column are stored sequentially. Although it's not majorly used, most of you have not probably heard of it, but it's a very common language among high-end developers, right? Or you can say a new language among high-end developers. So yeah, declaration and initialization are two-dimensional arrays typically declared by specifying the numbers of rows and columns. For example, in a language like C, a 2D array of integers with 3 rows and 4 columns might be declared as int, right? I will write int before of this, right? R 3, 4, right? So initialization, like one-dimensional arrays, 2D arrays can be initialized with values at the time of declaration, which creates a matrix of 3x4 or 3x3 with specified values. Accessing elements, let me give you an example of the initialization. if I write more and right. So this is an example. This creates a 3 into 4 matrix with specified values, right? So accessing elements, index-based access elements in 2D array are accessed using two indexes, like the one I've shown you for the first row and the first column, or the first for the row and the second for the column. Example can be R A R 2 3 accesses the elements in the third row and fourth column of the array. So modifying elements is just like one-dimensional arrays. You can modify elements in a 2D array by assigning a new value to a specific position. For example, you can specify the values using R 0 1 equals to 5 15, right? So it changes the value in the first row and the second column to 15. So common operations are like iteration to iterate through all the elements in a two-dimensional array. You typically use nested loops, right? One for arrows and another for columns. This is essential for tasks like printing the array, summing the elements, or applying a function to each element, right? Accessing the element is kind of different, and searching similar to one-dimensional searching. You can search for a specific element by iterating through the 2D array, though it requires checking each row and column pair. And then we have matrix operations. Two-dimensional arrays are often used to represent matrices in mathematical computations. Common operations include matrix addition, subtraction, multiplication, transposition, all of which involve iterating through the elements of the array. Then we have again memory management, right? In 2D arrays, contiguous memory allocation is done. So in row major, the elements of a 2D array are stored in contiguous memory blocks. For example, in the 3 into 3 matrix, the elements would be stored in memory as 1 2 3 4 5 6 7 8 9. This contiguity improves speed but requires careful indexing to avoid out of bound errors. In where memory overload, two-dimension arrays can require significant amount of memory, right? Especially for large matrices, each element's memory space depends on its data type. The total memory required is the product of the numbers of rows and columns. Then we have something called dynamic allocation. In some languages, 2D arrays can be dynamically allocated using pointers or referrers. This allows for flexible memory management, but it can also introduce complexity in terms of ensuring that the memory is properly allocated and allocated, right? So memory management is very important in programming, and not only in array but in other types of data structures and the whole programming concept, right? The whole software industry, because the memory management is important, because there is limited memory that we get. You won't be getting an unlimited 2 TB, 10 TB sort of memory allocations, right? So that's why memory management is important, same as money management and finance, right? So advantages of 2D array. There are some advantages of 2D arrays. Think of it like the natural representation of tabular data is one of the advantages of 2D arrays. 2D arrays are perfect for representing the tables, grid, and matrices, for similar to Excel's, right? So it makes them ideal for many scientific and engineering database applications, right? Efficient access and manipulation. They allow for efficient data access and manipulation, particularly when the data structure size is fixed and known in advance. Then you have some foundation for advanced structures. Two-dimensional arrays are foundational for more complex data structures like multi-dimensional arrays, tensors, image representations, right? So like one-dimensional arrays, the limitation of two-dimensional arrays are fixed size. One-dimensional arrays, the size of the for 2D array is usually fixed upon creation. This can be limiting if the exact dimensions are not known beforehand, or if the array needs to grow dynamically, right? And then something, if you have inefficient sparse data, right? When most of the elements in the data, 2D array can be R0 or unused. Memory management can be wasted. Sparse matrices where only non-zero elements are stored are more efficient in such cases. And complex indexing. While indexing is straightforward, managing multi-dimensional arrays, indexing is more like complex scenarios, like the higher dimensional arrays, and can become error prone and difficult to debug, right? So let me give you some real world examples so that you can understand better and give you a quick glimpse of what you can do. So images and graphics. In computer graphics, 2D arrays are used to represent images where each element corresponds to a pixel's color value. Then we have game development, right? Grids in games such as chessboards or maps or tile maps are often implemented using 2D arrays. Then we have matrices in mathematics, right? Matrices operations in mathematics such as used in linear algebra, physics, or machine learning. They are performed using 2D arrays. Spreadsheets, Excel spreadsheets, data in spreadsheets can be represented as 2D arrays with rows corresponding to records and columns to attributes, right? So imagine you are developing a game that involves a 10 into 10 grid, such as Minesweeper, the famous Windows game. Uh, I would have shown you, but I don't have it right now, right? It's a very famous and it's an old age game, which is like the oldest game I think in Windows. Right? A two-dimensional array can be used to represent the game board, right? Where each element in the array holds the state of a cell. Whether it contains a mine, is uncovered, or is flat, right? So do keep in mind some best practices. Initialize properly. Always initialize properly. Ensure that your 2D array is properly initialized, especially in languages that do not automatically initialize array elements, right? Consider memory usage. Be mindful of the memory footprint, especially when working with large arrays. Consider alternatives like sparse matrices or anything else if possible. Memory management again is very important. Memory usage is very important in this, right? Avoid hard coding. Instead of hard coding the dimensions of the array, use variables or constant. This makes your codes more adaptable to changes, right? Two-dimensional arrays are a powerful and versatile data structure essential for representing and manipulating grid-like data. Their ability to efficiently store, access data in a tabular form makes them invaluable in a wide range of applications. From simple data tables to complex mathematical computations, understanding how to use 2D arrays effectively, including their memory management and common operations, is crucial for any programmer dealing